Hello, everyone. Uh, Welcome to the first lecture of ECE3221, Computer Organization. We're going to spend the first lecture, maybe two, doing primarily review, covering a lot of content that you've looked at in the digital logic class in the past. Before we get into that, I just want to bring your attention to the notes that we're going to use for the class. So these notes, which are prepared by Dr. Turvo, were written specifically for this class. They're extremely well done. They focus on specifically the content that we are going to cover in this class. And I highly recommend that you read along in the textbook. Really, everything's relevant to the course. It's condensed nicely. There's some end of chapter problems that you might find useful, and just all around, there's really nothing in the textbook that's not relevant and that we won't touch upon probably at some point or other during the class. Just to kick off, we're going to basically start off in doing some review, which comes from chapter 1, which gets into talking about some basic digital computer fundamentals. One thing that we're going to keep coming back to as we go through the term is this diagram that represents in a pretty high level the key blocks of a computer. And this is shown here in figure 1.1, and we call it the computer organization, or the organization of a computer. Okay, so a lot of the class is going to be spent on understanding each of the elements that we see here in this diagram. And let me just let me pull these notes away, and we'll bring that diagram into our OneNote slides. Okay, so just to make reference to each of the blocks here, we're going to start by looking at some very basic digital logic components, things you've seen before, but review is always good, and we'll use those and put them together into as building blocks to the various components that we see in this diagram, starting with the registers. We will eventually work our way up to an ALU. We'll talk about input ports, output ports. We'll talk about memory, and then we'll talk about how the control unit works in this system. Okay, so you can see each of those small individual blocks. We can also focus on the processor itself, which is just made up of the registers, the control unit, and the ALU, or the arithmetic and logic unit. Or we can expand out to talk about the entire computer, which then incorporates our memory and our input and output ports, those things that give us access to the outside world. And then you see that label to the outside world called external, which really sometimes we kind of forget about these, the requirement for these external connections, but yet we interact with those external interfaces all the time in the various computers that we interact with on a daily basis, whether it's your desktop computer or your laptop computer. We've got outputs in the form of a screen, in the form of audio. We've got inputs in the form of a mouse, a keyboard, a trackpad, a touch screen. Much like our phones, we have inputs that are buttons, switches, the touchscreen on our phone, outputs, vibratory motors, speakers, the screen itself. Yeah, so we'll look at all of those kind of different things at a fairly basic level, and we are going to focus very heavily on a specific processor for this class known as the NIAS 2 processor, which is in fact a soft processor that is realized in the fabric of an FPGA, a field programmable gate array, which you all should be very familiar with from the digital logic course. But we're going to create an instance of a processor in an FPGA. We call that a soft processor or a soft core processor, in contrast to our more conventional processor, we may just call a hardware type processor. But we're going to use this soft core processor because it's fairly simple to understand, has a fairly simple instruction set. Okay, so let's move on, and as I said, we're going to start by doing a bit of a review. But one of the main things I always like to talk about, and I talk about this whether I'm teaching an electronics class or a digital systems class, is to know the difference between kind of the two realms, which is analog system and what the voltages look like in an analog system versus a digital system, where we're going to spend most of our time for this class. Okay, so if we're dealing with an analog system, which would be more common, said in an electronics class, if we were to plot these voltages in an analog system, the primary difference here is, the voltage axis versus time. The voltages, and this could be this could go negative. The voltages can really take on any value at any point in time, and those are kind of all the values around us in our environment tend to be analog in nature, although much of the digital world, or much of our world, has been digitized to represent these analog, whether they're voltages or temperatures or whatever the case may be. We tend to represent them with digital systems, but that kind of gets hidden from us. So an analog system or an analog value, thinking more generically, doesn't have to specifically relate to voltage. An analog value can occur at any instance in time, and it can take on any value. Okay, so it has infinite number of values that can be represented kind of on that voltage scale, if we're talking about voltages here, right? So, when you think about the temperature in the room around you, if you look at your thermostat, it probably says, maybe it says it's 22 degrees in your room, maybe it says it's 22.5. Well, that's in fact a digitized representation of the temperature, because in fact that temperature could be 22.1058, right down to a very specific value that is continuously changing. Okay, so the difference being when we represent digital voltages, in the most simplistic sense, we represent our voltages as only being able to have two discrete values. Okay, so the values can either be high or low. Okay, so this value here, maybe I'll use a different color here. This value here is representing a high value, or we may call it an on state, or more commonly we just refer to that as a logic level 1. Okay, whereas down here when the voltage level is low, so a low value, we might use that to refer to as an off state, or again more commonly in the digital realm we simply refer to that as a logic level 0. Okay, now this still could be a voltage axis here, but the specific value of these voltages might vary depending on the system you're using. This high level voltage value that's represented here, those values could be they could be 2 volts, they could be 3.3 volts, they could be 5 volts. It all depends on the specific standard of the system that you're working with. Okay, just like this low value. Now low value is much more common to simply refer to as 0 volts or something close to 0 volts, and we'll see here in a bit that it doesn't necessarily have to be precisely 0 volts. But again, for our purposes, we're going to primarily refer to states of a digital system by their bits, which will hold a value of 1 or 0. Okay, so again, we'll note the difference between an analog system and a digital system. Analog system, those voltages can take on any value at any point in time, whereas a digital system, and in this specific case, can only take on a value of a high or a value of low, a value of 1, a value of 0. It can only be 2 values, where that analog system voltage could be any value. Now we're going to see that as we put more and more concatenate more and more bits together, that we can represent more and more steps in our digital system, more and more resolution, more different quantities, and that's often what is done in digital systems. By having numerous bits to represent a value, we can get more precise representation of an analog value with a digital system. Okay. When we think about focusing on the digital system, when we think about binary values, binary logic tends to be considered to have either a true or false state, and we'll again come back and revisit this as well, but generally a true state is represented by a 1, and a false state is represented by a 0. We're going to come back and revisit this later, and we're going to see that often when we're doing when we're doing a conditional, writing a conditional statement that's checking to see if something's true or false, true simply means non-zero, whereas false means 0. Okay, so as we get with a single bit, non-zero simply means 1, but as we get more and more bits, they don't necessarily all have to be equal to 1 for the condition to be considered a true. Okay, so we'll come back and revisit that. Let's talk very briefly about Boolean algebra, something that is also a review. Okay, so if we let the letter A be a digital signal, then A can have a value of 1 or a value of 0. Okay, so let's talk about what happens if we do a NOT operation on that value of A. Okay, so a NOT operation on the value of A means that if A was originally equal to a 1, then not A, so A with a bar over it is how we represent not A, is going to be equal to 0. Okay, very simple, something that everybody has seen before. If A started as a 0, then not A would be a 1. So it's just the inverse of the original value when we do a NOT. Okay, this nodding operation is done with a device known as an inverter. Okay, so if I put that digital signal A into an inverter, at the output I'm going to get not A. This device that I've shown here is what's known as a logic gate. Okay, this specific logic gate has one input and has one output. The bubble here that's shown on the output is a means of indicating that a NOT operation is occurring. Okay, so this bubble is indicative of a NOT, and we're going to see that the bubble can be used on the input, can be used on the output to show that the signal as it goes through that bubble gets inverted. Right? Because I could also have a device that looks like this. And your first reaction might say, oh, that's an inverter. But it's not. There's no bubble. Right? So if I put A into this, I'm going to get A out. I should make my signals a different color here. Okay, so up here I put A in, I got A not out. This device that I've shown, I put A in, oops, I get A out. Right, so no change in the signal. This is what is referred to as a non-inverting buffer. Okay, so what's the point? If we are getting the same signal out as we put in, why bother putting this device in the circuit at all? Well, a non-inverting buffer is a device that, for maybe lack of a better term, can strengthen our signals. Okay, we'll come back and revisit this in a bit, but we'll see that logic gates have a limited capacity to supply current from their outputs, and buffers can act to provide additional current capabilities from the output. So maybe you have something that you need to power from the output of your digital device that whatever the device is, you can't drive that directly. Maybe it's an LED would be a common example. So you might use a non-inverting buffer, so it doesn't change the logic state of the signal, but it does provide more current capability. So it acts like a amplifier. Okay, when we talk about digital logic circuits, we talk about two primary different classes of circuit. Again, review for everyone, but we'll go over them briefly here just as a reminder. So the first class of circuits is combinatorial circuits, sometimes referred to as combinational logic. Okay, this type of circuit, logic circuit, the output is formed from a combination of inputs. Okay, some examples of this. The logic functions that would be included are things like and, or like the logic gate up above here, that inverter would be a combinatorial logic circuit, a NOT, NAND, NOR, XOR, XNOR. Okay, so those type of circuits that we apply some logic state to the input, and we, as a result, get an output formed. Okay, and let's review some of these combinatorial circuits, like our AND gate. So our AND gate is a device that has two inputs that combine together to form one output. Okay, and our logic is that the output is the A and it with B, and so that dot there is signifying an AND operation. Sometimes when we write our Boolean logic, we just leave the dot out and just show an AND operation like this. The truth table for an AND gate, oops, looks like this. Okay, so my, oops, sorry. The logic states of my inputs shown on the outside here, and just as the gate, the name of the gate suggests, I have to have logic level highs at both inputs, right? I need a high or a logic level 1 at A and B. So that is the only case where I will get a logic 1 on the output. If I have 0 and 0 on the input, I get a 0 output. If I have 0 and 1 on the input, I get 0 out because they're not both high, or if I have a 0 and 1 the other way. Okay, so again, something everyone has seen before. Let's review another one. Let's make a modification to this gate and look at a NAND gate. Okay, so a NAND gate is basically an AND gate that has its output inverted. Okay, so this is an AND gate where at this point we have A and B, and at the output we have A and B knotted to form C. We don't typically show our NAND gate this way. We show it simply as a AND gate with a bubble on the output. So there's that bubble again, signifying that inversion operation at the output. Okay, so A, B on the input combine to form C on the output. Truth table for this looks very similar to what we saw for the AND gate, except everything's inverted on the output. Okay, so 0 and 1, 0 and 1. So we look above. Up here for our AND gate, this is what we would have seen on the output. Well, actually, right here is what we see on the output. The output of the NAND gate goes through a final inversion, so all of those outputs will be the inverted form of what we saw with the AND gate. Okay, keep going. The review here, let's look at an OR gate. Okay, an OR gate, the symbol you should be familiar with, looks like this. Okay, where A and B on the input combine to form C on the output. The output C is A or B. The plus symbol signifies an ORing operation, and just as the name suggests, the output is formed through a combination of the inputs, where if any one of the inputs is high, right? If A is high or B is high, we will get a high on the output. So the only case in this truth table where we get a low is when neither one is high. But if A is high, we get a 1. If B is high, we get a 1. If they're both high, we get a 1. Okay, NOR gate again is just our OR gate with an inverted output. See that bubble on the output signifying an inversion operation. So A and B are combined to form C. So we have A or B knotted. Truth table in this case is just going, the output is going to be the inversion of the truth table of the OR gate that's shown above here. Right, so when again, I find it simplest just to think about what the output of an OR gate is and then just invert that. So here in highlighted in green, we see the output of the OR gate. The NOR gate would just be the inversion of that. Oops. right? So every signal inverted. One final gate we'll look at, just again as a review. Actually, let me draw it from kind of the fundamental components here first. If I take two AND gates, feed their outputs into an OR gate, and take the inputs to these AND gates and form them from the one input and the inversion of one input. Okay, so B input and the inversion of B input. Okay, so got A, B. Here I'm getting A naught and B naught. Okay, so A here, B is here. So at the output of the top AND gate here, I get A and B naught. Here I get A naught and B. And finally at the output C, I get A and B naught, or A naught B. So if this combinational or combinatorial logic equation doesn't look familiar to you, this is what we refer to as an exclusive OR, or more often just called XOR. And of course we don't usually draw all the individual gates. We typically show an XOR. Oops, sorry, let me try to do an XOR that looks like this. Okay, A, B, and the XOR symbol we use is a plus inside a circle. The reminder of what the truth table looks like for an XOR gate. An XOR gate, if you look at the maybe this logic equation up here might make it most obvious. It's saying that the output is only going to be high when A is high and B is low, or when A is low and B is high. So in other words, when the two inputs are different. Okay, so showing that in a truth table, let's say this is A and this is B. The only time when the output is high is when the inputs are different. So here I've got 0 and 0, so those are not different, so I get a 0 in output. Here I get a 1 and a 1, again not different, so I get a 0 in the output. But here I get a 0 and a 1, those are different, so I get a high. Here I have a 0 and a 1, those are different, so I get a high. Okay, so again, you might be thinking at this point, why am I reviewing this very basic these very basic logic gates? We spent a lot of time in digital logic investigating these. Well, for this course, I want us to think about using these logic gates and these logic operations in a little bit different application, more in the application and how they might be used in a system to manipulate bits or to control the flow of data. Okay, so on that note, let's come back and revisit our AND gate here. Okay, so if we think about an AND gate again, and we remember that an AND gate only lets the output go high when both A and B are high, right? A and B have to be high in order for C to be high. So let's think about this slightly differently. It's really the same way, but I just want you to frame the way you think about this a little differently. If B is 0, then we immediately know that C must be 0, right? Because if any one of the inputs is 0, the output has to be 0. And this is going to be the case regardless of the state of A. Right? If B is equal to 1, then what's C going to be equal to? Well, C is actually going to be equal to the state of A. Right? B, if my signal B is high, A will determine what the state of C is. Right? If A is low, well, I don't have them both high, so C is going to be low. If A is high, oh, they're both high, so C is going to be high as well. Okay, so thinking about this AND gate from this perspective, you can think about B as being a control signal that determines if A gets through to the output or not. Or thinking about it as another way, B can be used to force the output low, right? Like in that first case, right? When B was low, we force the output low regardless of what was happening with A. Okay, so this can come in handy when you're trying to manipulate bits in your system. If you want to force a particular bit to be low, you can take the original bit, AND it with a 0, and you are now going to force the resultant or the output to go to 0. Or again, thought of it another way, if I use B as a means of determining whether the signal gets through or not, right? And we might use this AND gate as a gating device to decide whether the signal that's coming from somewhere else in the system is allowed to get through, right? If that signal that's tied to A might, B could be used to determine whether it gets through and connected to C. Okay, so really we haven't looked at anything new, but just maybe changed our perspective on the use of an AND gate. So let's think about an OR gate kind of in the same kind of way. I'm having a horrible time drawing a nice OR gate here today. Okay, so here's my OR gate, has inputs A and B, and then output C. Let's think about this OR gate in a similar way as we did above. Well, if B is equal to 1, then my output C is going to be 1 regardless of what is happening on A. Whereas if my B is a 0, then C is going to be equal to A. Okay, so we might use an OR gate or an OR operation to force an output high. Okay, so if we have a bit in our system that we want to force it to be high, to ensure it to be high, we can OR that bit with a 1 and the output will be forced high. Okay, let's continue to look at our use of these logic gates in this way. Let's look at an XOR gate. Okay, so recalling that an XOR gate only sets the output high when the inputs are different, right? So if, again, thinking about using B as a control signal, if B is 0, then C will be equal to A. Okay, let me draw the truth table again here to convince you of this. Remember the truth table for my XOR gate looked like this. This was A, this was B, and my output was only high when the inputs were different. Okay, so look at this first statement here. When B is 0, when B is 0, look at the output. The output is going to be the same as the input, right? Right here. Output C is going to be the same as A. If it's A is 0, the output will be 0. If A is 1, the output will be 1. Okay? What about if B is 1? Well, if B is 1, then the output, let's look at that. If B is 1, then the output is the inverse of A. So C will be equal to A bar. So looking at use of an XOR gate in this way, we see that B can be used to determine if A gets inverted or not. Okay, so another way we might think of this might be thought of as a programmable inverter. So a gate where we have a control signal, in this example B, that determines whether the gate is going to invert the signal or not. Okay, so let's look at this in use with a few simple bitwise logical operations. Okay, so let's do some simple bitwise logical operations. Bit, let's see, bitwise. Bitwise meaning we're doing it on bit by bit. Okay, so if I take, I'm gonna use the same 4-bit value for A. So I'm now assuming I have 4 bits in my system. Each one of those bits can be a value of 1 or 0. Okay, so the first operation I'm going to show is a NOT operation. Okay, a NOT operation is an operation that only has a single input, right? Think about our NOT gates up above here, right? This NOT gate only had, up here, only had a single input, right? So that type of logical operation is what is often referred to as a unary operation, which refers to an operation with a single operand. Okay, so a NOT operation, if we have a value of A, and let's assume that value of A is equal to 1100, again a 4-bit value, and I perform a NOT operation on that, my output is going to be the inverse of each of those values, right? I've inverted, I've NOTed each bit in my bitwise NOT operation. Okay, let's use the same value of A and do a bitwise OR operation. Okay, so remember up above here we said that the OR operation could be used to force an output high. Okay, so, or another way to think of that, about that is we use to selectively set bits. And when we talk about setting bits, this means making equal to 1. Okay, so let's take that same initial value of A, which was 1100, and then let's use a value of B that's going to selectively set the least significant bit, the farthest bit to the right. So 0001, this value of B is going to selectively set the least significant bit while having no effect on the other bits. Okay, so in this when using an OR operation, the zeros have no effect on the input as it goes to the output. Okay, just go up here and remind yourselves that again, right? If we have a 0, the input, the output just tracks the input of A. Okay, so following through with this, A or B, we OR these two values, 0 and the 1 result in this bit selectively being set high, right? This original bit in the, if we assume that B is the value or the value in the 4-bit value of A is what we're manipulating, we want it to selectively set the least significant bit to selectively set the least significant bit, or make that bit equal to a 1. So by ORing with a 1 in that B field, we've caused the output to go to a 1. The other bits of A remain unchanged, right? Because as I said here, zeros have no effect. Okay, so we've selectively set the least significant bit of A. The rest of A has remained the same, 1, 1, 1, 0. The least significant bit we selectively set or made a 1. Okay, let's think about using the bitwise AND operation. Okay, let's go up here again and think about what we said about the bitwise AND. The bitwise AND, we said, can be used to force an output low. Right? When we put a 0 on the B, the output is low, regardless of what is on A. So we can force the output to go low, independent of what's happening on A. So another way of putting this might be that a bitwise AND operation can be used to selectively clear bits. Clear meaning set equal to 0. Okay, so let's have a look at how this works. If I start with my original value of A again, which was 1100, and I AND it with a value of B, and now I want to force the most significant bit to be cleared. Okay, so I put a 0 when I'm doing an AND operation. I put a 0 where I want to clear a bit, and I put a 1 where I don't want to have any effect on the bits. Okay, so now A AND it with B will give me an output where 0 and a 1 AND it together, I get a 0 in the output. That's the same as I had on the input A. 0 and a 1, I get a 0 in the output. That's the same value I had at the beginning. 1 and a 1, I'll get a 1 out. So my value that I will put into A stays the same on the output. But here I have a 1 and a 0. 1 AND it with 0 gives me a 0 on the output. So I've taken that value that was originally a 1 and I've forced it to be a 0. So I've selectively cleared, in this case, the most significant bit. I'll also have you note that in a AND operation, the 1s have no effect. Right? Where the OR operation, we said that the zeros have no effect, and with the with the AND operation, the 1s have no effect on the output. Okay, let's look at one final one before we wrap this up. About a bitwise XOR. Well, as we stated up above, a XOR, use my highlighter, can be used as a programmable inverter. Stated another way, we can use an XOR to selectively invert or complement, another word for invert, bits. Okay, so let's look at an example of this. We'll start with the same initial value of A, 1100, and we will put a value of b such that we want to complement this value. We don't want to complement this. We want to complement this value. We don't want to complement this. Okay, so here A XORed with B results in 1 and a 1, so the values are the same, so we get a 0 out. Different values get a 1 out, different values a 1 out, same values we get a 0 out. So here again we'll notice that wherever we had a 1, we inverted the bit from the input to the output, right? 0 here became a 1 here. Okay, so in the XOR operation, like the OR operation, the zeros have no effect on the output, but the ones cause a inversion in that bit.